Greetings, guys. So now we want to talk about triple integrals. Triple integrals is just the next natural step after double integrals. We've already talked about the double integral is a symbol that we use to talk about a sum of area pieces, right? So sort of the same idea with triple integrals. Instead, we'll be adding up over an entire region of space, over a volume, if you will, right? So basically, we're just going to be summing all of the values of a function, just like any other integral would normally do. But instead of just in a line or just in an area, we'll be doing it inside of an entire volume. And that's what a triple integral actually does. Okay? Now, just like the double integrals, we'll be converting the triple integrals into 3 iterated integrals. Instead of 2 for doubles, it's 3 for triple integrals, naturally, right? So I'll be converting a triple integral into 3 iterated integrals. And for this section, we'll be talking about the rectangular form of this, right? So here's one example of how that could come about. I could have an iterated integral such that my incremental volume differential piece is split into dx, dy, dz. And remember what that means is the inside integral here will be dx, right? So this will be a dx integral. And then, of course, the next one will be dy. And then the last one, of course, would be dz. And then you can see the corresponding limits on each integration. When I'm doing the first integral on x, it is entirely possible that the boundaries on my integral can depend on both y and z, right? So I have a function of y and z here, and I have a function of y and z here, possibly, or it could just be numbers, okay? But this is what could happen. And then as I go outwards, I slowly lose variability, right? After dx is integrated, and then I have to move on to y. Y could be dependent on z, and then notice the last bit, z is just going to have the values to finish up that integral. Okay, so then some other little pointers here. If you remember from Calc 1, when you're doing an integral with dx, you're literally just finding a length, right, on the axis that you're counting. And from a few sections ago, when you do a double integral, just dA over some region, then all you're calculating is the area in your domain plane, right, inside of that region. The area inside of that region from your domain. So a similar idea should also be applicable to triple integrals. If I'm doing triple integral over some region of space, Q, right, and all I've got in here is dv, no actual other function to multiply in, then I'm just going to be finding the volume of the region of space that I'm integrating inside of, Q, right? That's all I'm going to be finding if I'm just doing triple integral dv. If I'm doing a triple integral with a function, however, right, notice I'm distinguishing that from this. If you're doing a triple integral of a function, it's very likely you're not performing a volume, or if you are, it'll be of something else, okay? What you're actually doing with these is you're adding up over the entire volume the values of some function. For example, maybe you want to find out the total temperature area energy in an entire region of space, and you've got some function that tells you the temperature at each point in this region. That could be a triple integral where you want to add up the total temperature energy maybe, or maybe you have an electric field passing through a region, and you have this region, then you're going to integrate all of the points in it, and your electric potential function is the function. Whatever the application may be, if you're integrating a triple integral of some function, you're adding up all of those function values in that volume region that you have chosen with the boundaries given. Okay? So no function, that's finding just the volume of a region. Okay? Bringing in another function, You need to remember that's not necessarily a volume, and you need to keep the region in your mind separated from the actual function itself that you're integrating. Okay? First example. Here's a triple integral that's already been converted into 3 iterated integrals. And we're just going to talk about the features here and work it out. See how it's pretty much the same thing that we've been doing since we've been talking about double integrals as well. Right? Key feature. Notice the difference between the function that I'm integrating, in this case y, between the actual bounds and the region that I'm integrating over, right? Here, 0 to xy are the boundary pieces for z, right? That's dz. And 0 to 1 plus square root of y are the bounds of x. And then 0 to 1 are the boundaries for y, right? So notice as we go along, right, the first variable can depend on the other two. The second variable can depend on the last one. And then the last one should be just values. Okay? So let's go ahead and do these. I'm just doing the antiderivative of y dz. Y has no z dependence in this case. So we just have integral from 0 to 1, integral from 0 to 1 plus square root of y, y times z evaluated from 0 to xy, dx dy. Okay? So then, of course, I'm going to plug in the xy and the 0, right? This piece right here is just going to be xy minus 0, which is just xy, right? Xy times y is going to give me xy squared. Okay, now we're back to familiar regions, right? A double integrated integral. Okay, so then I'm just going to continue from here. Antiderivative of xy squared dx. Does the y squared, again, is not a part of that integration. I'm just antiderivative of x dx. So from 0 to 1, right, y squared, and then antiderivative of x is 1/2 x squared, and that's going from 0 to 1 plus square root of y, and then dy. Okay? All right, so from here, I'm going to go ahead and pull the 1/2 out, get that out of the way, and I'm going to plug in these two things, right? So notice when I plug in the 0, of course, it's 0. Minus 0 doesn't do anything. And then when I plug in this guy right here, I'm going to have a binomial I need to square. So let's continue. Going from 0 to 1, I've got y squared times 1 plus the square root of y squared dy. Minus 0, right? Doesn't change anything. So then, of course, this is one of your basic integrals from Calc 1. I'm just going to FOIL, distribute out everything, and then do all of my power rules, right? So 1/2 integral 0 to 1 y squared times 1 plus 2 square root of y, and then plus y. Distribute my y squared. And don't forget, square root is y to the 1/2. So let's go ahead and rewrite that. This is y to the 1/2 power, right? Okay, so that'll help when I'm multiplying here. Plus 2, and then that's going to be y 4/2 plus 1/2, 5/2. And then of course y squared times y is y cubed dy. All right, next, 1/2, and then I have a 1/3 y to the 3rd plus, now I have 2 times, right? And that's going to be y to the 7/2 there, right? Y to the 7/2, because I'm adding 1, right? And then I've got to divide by that. So 2/7, like so. Okay. And then lastly, I've got 1/4 y to the 4th. And that's being evaluated from 0 to 1. Okay. Well, in our favor, right? If I plug in 0, all those are going to be 0. And also in our favor, if I plug in 1, it's just times 1 with all of these powers, right? So I've just got 1/2 times 1/3 plus 4/7 plus 1/4 here. Right? 2 times 2/7 gave me the 4/7 there. Okay. So I just need a common denominator here between 3, 7, and 4. Let's do that. Whoops. Okay. So let's see. 3 times 7 times 4 is going to be 84. Nice. Okay. So then I've got 28. And then I've got 48. Right? And then I've got 21. Okay. So let's add all these up. I get 16, 17. Right, 17, carry 97. Okay, so then I've got 97 over 168. Right? Okay, so this first example, like I said, was just to get the idea that a lot of the mechanical pieces that we're doing are still the same as with the double integrals. Okay? Okay, next example. Find the volume bounded by x equals y squared, x equals 4, z equals 2 plus x, and z equals 0. So we've been given a few surfaces here, and we're going to intersect them, and then we want to find the volume that's trapped inside of that intersection, right? So don't forget, if we're doing an integral for just a volume, then all we'll be doing is a triple integral over the region dv, right? This is all that we're going to actually be doing. But then we're going to want to convert that into our iterated integrals, okay? So sometimes it also helps to get a visual. Let's try to draw it out for a second, and then we'll go take a look at what it really looks like. So I'm going to be doing this integral, but so I can convert it into an iterated integral, let's draw the image here. So here's my z-axis, here's my x-axis, here's my y-axis, right? My z right here. Okay, now z equals 0, right? And all of these things are probably positive, right? The way things are adding, and x is positive 4 here, and things like that, right? So we have our plane, right here, the XY plane, that's z equals 0. So it's going to be everything sort of above that. X equals 4, right? So let's mark that out. Here's x equals 4. And x equals 4 itself is a plane, right? Okay. Then I have x equals y squared. So what I'm going to do is I'm going to draw the y-axis a little bit more right here. There's my y-axis. And x equals y squared should sound very familiar to you, right? Because y equals x squared is something we see a lot in algebra. It's a parabola, but it's the curve, on the xy plane to start with. And then since there's no z variable, it's actually a parabolic cylinder, right? So I draw the parabola, that's the relationship between x and y. Which is going to look something like this, right? And then we're talking about the cylinder that comes up from that, right? So the cylinder here. Right? It's a parabolic cylinder coming up there. So I've got the plane on this side and the cylinder's here, right? I've got the cylinder like this up against the plane. Okay? And then z equals 2 plus x. That's also a plane, right? Z is to the 1 power, x is to the 1 power, and there's no y variable in it. So it's going to have some sort of a relationship between z and x, right? And the y is basically going to just go side to side. Okay? So to make that one work, we talk about the z equals 2 plus x. That would be like this. If I were to put 2 marks on z here, right? Z equals 2. And then have an x slope going into the x plane like this. Right? And it's going backwards from it as well. And then the plane itself is coming across here. So what's actually happening is you're getting your parabolic sheet and the plane is slicing it like this, right? Because the z line with x is coming into the x-axis positively this way. So you're actually going to get like a parabolic slice right here. Like this. Whoops. So you're actually going to get this little slice like this. That goes along with that line. Like that. And then it's going to be this region in the parabolic cylinder underneath that slice, right? So we'll have the parabolic cylinder and we'll slice in it like that. Okay? So my drawing is only human. Why don't you take a look real quick at what it really looks like. Here's our rectangular coordinate system. We're trying to find the volume inside of the shape that's between these surfaces here and the z equals 0 plane. So let's go through these one at a time. We have the important shape here, of course, the x equals y squared parabolic cylinder. And there it is. Just parabolas all straight up and down the z-axis there. And then we also have our x equals 4 plane, which slices right into our parabolic cylinder. So you can already see a region forming here, right? And then, of course, the final surface, this plane right here, that slices at an angle through our region right here. So as you can tell, it's going to be this piece inside of here.
However, it's kind of difficult to see this way. So let's take a look at the surfaces one piece at a time. Okay, so let's get rid of that plane, and there's the back wall of it right there. Let's take care of this piece is the bottom of the region. Okay, then we have the top of the region, which is the same as our plane here, right, slicing through that piece there. And then the parabolic cylinder itself only has those wall pieces there. So we're actually finding the volume of this object here.
Let's talk about how we can get our boundaries here for the iterated integral. We're doing the region inside of this thing here, okay? So then I want to set up my integrals so that everything flows like it's supposed to, right? Okay, so then I'm going to set up my 3 iterated integrals here. Here, right, like this. And it's just going to be dv, okay? So then I'll put my differential pieces out here, right? We need to talk about the order that we're going to do these things in, right? The order that we're going to do them in is actually going to be, let's see. Let's try dz, dx, dy, right? dz, dx, and dy, okay? The y values here are easy to get your numbers from right here. You can see right here that y is going to vary from -2 to 2. Right? X is already a function of y on one of the boundaries. So that's why it was easy to make x the next integral, right? X is going to go from, remember I need to be inside of the figure here, so x is going to be inside of the parabola here. The bottom value is going to be the y squared, and it's going to go up to 4 because the x is coming inside of the curve here. It's got to go from the parabola up to that maximum value of 4 in here, in this parabola here. Okay, so y had to be x had to be a function of y, right? Which is why x had to be the next one of the next integrals up. And then z, right? Z is a function of x, right? Because z is equal to 2 plus x. Z, the z value that you're doing all around the outside and in the middle is going to depend on where you're at with your x value. So z is going to start on the plane at 0, and it has to go up to this surface 2 plus x. Like so. Okay, so now we've got our iterated integral, right? So then we can start evaluating that one piece at a time. Let's start with the dz portion, right? This portion right here is just going to be z evaluated from 0 to 2 plus x. Okay, so that's a pretty straightforward piece. I have integral from -2 to 2, integral from y squared to 4. 2 plus x minus 0 is just 2 plus x. And then I have dx and then dy. Okay? Next, I'm doing the antiderivative of 2 plus x dx. So -2 to 2, still the integral for my y there. And then the antiderivative of 2 plus x is just going to be 2x plus 1/2 x squared, evaluated from y squared up to 4 dy. Right? Okay. So now we're going to substitute those pieces in. Integral from -2 to 2. And then I'm going to have, let's see, 8. And then 16 over 2 is 8 again. And then 2 times y squared, but it'll be minus. And then minus 1/2 y to the 4th. Okay? So now I do my last antiderivative. This is technically 16, right? So I'm going to be doing the antiderivative of 16 dy there. 16y minus 2y squared antiderivative. I have minus 2 over 3y cubed. And then minus 1/2 y to the 4th antiderivative is going to be minus 1 over 10 y to the 5th. And we're going from -2 to 2. Okay? Last little bit of substitution here. Plug in my 2. Let's do each one individually. Let's do that. I have 16 times 2 minus -2, right? Because I can do top minus bottom here. Minus 2/3 times, that's going to be 8 minus -8. And then minus 1/10, I'm going to have 32 minus -32. Okay. 16 times 4. 64 there. Minus 2/3 times 16 again. Minus, and then I've got 64 over 10, which I can reduce to 32 over 5. All right. Okay. 16 times 2 over 3. Let's go ahead and simplify that a little bit. Save some space here. That's just going to be 32 over 3. And the common denominator that I need here is 15. Let's see, I can make this really easy on myself, huh? I could factor out that 32. That would leave me with 2, right? Which is 30/15, right? 2 is 30 over 15. I factored out the 32, so that's 1 over 3, but multiplied times 5. So minus 5/15. And then right here, factored out the 32, that would be 1/5, but times 3. So 3/15. So I'm left with 32 times, I've got 22 over 15, right? Because that's 30 minus 8. So I've got 640 and 64. So 704 over 15. Okay. All right. So remember what we just did here. We found a volume using a triple integral by just doing the triple integral with a dv and keeping the appropriate bounds. So the volume that we found is actually the one that's inside of that parabolic cylinder underneath that slanted plane over the top of it. Okay? Next example is we're going to integrate a function inside of a region this time. And one of the key things that I want you to notice, especially with the final answer, is that we're not actually finding a volume here. Okay, we're doing a triple integral to actually sum the values of a function inside of a region for whatever reason our applications require. Okay, so here we go. We're going to integrate the function of 3 variables, right? It's a function of 3 variables, x cubed, y cubed, e to the z. And then we have a region in space bounded by these surfaces, right? Z is going to be underneath the 1 minus y squared, right? Z equals 0 is going to be our bottom, the plane. And x is going to be bounded between -1 and 1. Okay? So let's take a look. Z equals 1 minus y squared. Well, think about what that would have done in normal two-dimensional algebra, right? Something that's equal to 1 minus another thing squared. That's a parabola facing down and moved one up, right? Okay. So that's between z and y. That means it looks like this, right? Just in the zy plane, that would be the slice of it, okay? But there's no x variable, right? No x variable in there. Again, that means it's going to be kind of like a cylinder, right? And it's going to take that shape and it's going to just drive it all the way along the x-axis. Okay? So again, we're looking at a parabolic cylinder, right? Doing this. But only between -1 and 1 on x is allowed. Okay? So if I put 1 here and -1 back here, on my x-axis, I put the boundaries for x. Okay? Now let's draw some more of the surface. I'm going to have something along here. To here. And then right, so it'll be going along that piece of the axis there, of the plane, I mean. So we're looking at this surface like this, right? I've got this parabolic cylinder surface, and it's got to be above the xy plane, right? So it's hitting the y-axis right here, right? If you let z be 0, you'll notice that y is both 1 and -1, just like x is. So we told x to be from -1 to 1 so that the cylinder wouldn't go on forever, but naturally being above this plane restricts y, its own self, between 1 and -1. So right here, this is 1 on the y-axis, and right here, this is -1 on the y-axis. And I'm underneath this parabolic hood, if you will, right? Almost like one of those weird parking shade things, right? Or a planting dome or something like that. Okay? And we're going to be integrating this function all throughout that volume. Okay? So real quick, take a look at a real better graph than mine, right? What it really looks like.
Here's the function z equals 1 minus y squared. As you can see, it's a parabolic cylinder that stretches along the x-axis here, basically parallel with the x-axis, and it's just shifted 1 up on the z as expected. We're not interested in the whole cylinder though. We were restricted on our x-axis from -1 to 1. So I'm only looking at this piece right here of the cylinder, right? And not even the piece that goes below the plane, because it even said z has to be greater than 0, or z equals 0 was one of our boundaries. So technically we have this floor here as well to this piece. Okay. Remember, we're not actually integrating for a volume on this one. We're integrating the value of that function in all of the points inside of this region here. Right? We're trying to determine just a total sum of whatever that function is listing for us. Okay.
So let's actually calculate the value of these functions, the total value underneath this surface, right? Let's set up our triple integral. Over q, x cubed, y cubed, e to the z dv. So I'm doing my triple integral, right? Summing up all the values of that function inside of this region of Q. All right? Well, that means I need to set up the iterated integrals now. Okay, so got my three integrals. My function is still there. And then I'll have my three differentials to go along with it, right? Well, y and x are just bounded by numbers. Obviously, x being the most extreme one, it was given to us, -1 to 1. So dx will be the most outside one here. And then as a consequence of being above the plane, right, y is also bound from -1 to 1 because that's where the z surface hits the plane. Okay? Then there's z is being bound from the plane 0 up to the function 1 minus y squared. Right? So I'll be doing this these iterated integrals. Oops. Y, z. Right? Z is the most inside, then y. Okay. So my first integral is just dz. The only thing that's being affected is the e to the z. And in fact, this x cubed can go out two of them, right? X doesn't happen until the very end, and it's just multiplied constant, basically, until then. So I can do this. Antiderivative of e to the z is e to the z, and it's going from 0 to 1 minus y squared. And I still have my dy and my dx, right? Okay. So then at this point, I'm going to go ahead and do my plug-in and subtraction. Remember, e to the 0 is 1, not 0. So it will actually have a -1 in there. Let's go ahead and get this pesky x integral out of the way. Notice there's no dependence on x anywhere else, right? So basically this is going to become just a multiplied iteration, right? As we've seen a few other times. One of those times where you can completely separate it out. So I can get that piece out of the way. And then times my other integral from -1 to 1. I have y cubed times e to the 1 minus y squared minus 1 dy, like so. Okay. To make that second integral easier on myself, I'm going to multiply the y cubed in here. Distributing it out, right? Go ahead and make that a bit of an easier process for myself. This integral right here, we can quickly knock out. And same thing with this guy over here, right? The integral of x to the third from -1 to 1 is 1/4 x to the fourth. And then I've got -1 to 1 here. Okay. Notice what I'm actually going to end up with here is, just for this piece right here, is 1/4 times 1 minus 1, which is 0. And you could expect that anytime you have an odd function integrated over symmetric pieces, right, from -1 to 1. And actually, you can expect the same thing from this one as well, right? This integral right here is also going to end up being 0. This piece right here. Okay, so then notice what I have left is 0 times the integral from -1 to 1 y cubed times e to the 1 minus y squared dy. Okay? And it will take some doing for you to notice this, but the value of this integral is actually also 0. Right? So we're actually getting 0 times 0. And that's because this is also an odd function, right? The y cubed is odd, and the e to the 1 minus y squared is an even function. Okay? So I've got this odd shape, and it's over symmetric limits as well. So what we're ending up with here is 0 times 0. If you're not sure about that, you can actually integrate this using by parts, but you'll have to separate one of the y's for the antiderivative of e to the 1 minus y squared, and then use the, you would have to do it like this, just real quick. If you're actually going to try integrating this, you can go, for your own sake, make sure you're up on your game. Just let your u be y squared, and let your dv be y times e to the 1 minus y squared dy. Right? Find your v, find your du. Go ahead and do your by parts for this guy. But then, of course, at the end, you'll notice that you do actually end up with 0 for that one. Okay? But I got us out of it easy, right? 2 of the other pieces are already 0. And then 0 times 0, of course, I'm getting the value of 0 for my integral here. Okay? So what's the point of this? I wanted to point out that it is entirely possible to integrate one of these things and it end up being a negative or 0 or something other than what you may expect. Because again, we're not integrating to find a volume here. This is a total value of some function inside of a region of space. Okay? One more example here. We want to talk about what happens when you need to change the order of your differentials in doing one of these multi-layered iterated integrals, right? It's not always as simple as, oh, just write dz and dy in the backwards order and just swap a couple of the integrands, right? It's not that simple if they actually have interlinking dependence, right? If one of the integrals is dependent on one of the other variables. In this case, z is dependent on y, right? And then dy is dependent on x. X, of course, has the numbers there. If I want to rearrange it, say, to dx, dy, dz, that's going to pose a big problem since it's sort of a domino effect here, right? Moving x to the front may not be a problem with the numbers, but then doing dy after I've already computed x is not going to work, right? Because it has a dependent on x. It needs to be inside of that. So I would need to flip-flop the x and y dependence, right? But then also, if I'm doing, z on the outside, I need to have that dependence of z already taken care of as well. So I can't just switch the letters up to make this work the way we want it to, right? It's not about just changing up the way we write something, okay? We need to understand what's going on in the region and how I can look at it basically from a different angle, okay? So I'm going to draw some of these things out, and then you can take a look at what it really looks like in a second, okay? We have that z goes from 0 up to the square root of y squared plus 4y. Okay, well, z equals 0, and then we also have z equals square root of y squared plus 4y. Okay, it may not look like it, but this is actually the equation of the top half of a hyperbola. Okay, the top half of a hyperbola, that basically does this. Like this. Okay, and if you're wondering how we can do that, the first thing you do, of course, is square both sides. And then complete the square on y squared plus 4y. That will give you y plus 2 quantity squared minus 4. Yeah. So then from there, what I would want to do is flip-flop these things around, right? I would have 4 equal to y plus 2 squared minus z squared, and then divide everything by 4. Which is the equation of a hyperbola where the distances of each of the main branches are 2 and 2, because it's 2 squared and 2 squared, and the y-axis has been shifted left 2 for the center. So right here at -2 is the actual center, and you'll find that these lines have a slope of 2 over 2, right? You have your little asymptotes that you draw your hyperbolas with. So essentially you get this hyperbolic shape. It's probably a little bit steeper than that, right? More like that. Same thing here, like that. And it's only the top half because in our actual integral we're only using the positive half of that, right? Okay. Now as you can probably tell, I'm only going to be using this piece of it right here, right? For that particular graph that we're doing, that region, okay? Now what about the dependence between y and x? Well, from the dy here, it goes from 2x up to 4. Okay. Now I've rotated the axes a little bit. This isn't traditionally how you would look at an XY graph from college algebra or pre-calculus, but if you think about it, we do kind of need to visualize it this way so that we can generalize it out to our 3D, version of it here. So all it is a rotated version of x and y. So we have the equation y equals 2x, which is just a line, right? Just a line. Y equals 2x. It's going to go like this. Right? Like this. Okay? But it only goes up to 4. So if I say this is 4 on the y-axis here, right? Then I've got my line, y equals 2x, and it only goes up to this point. And the region that we're talking about is from 2x up to 4 in the y direction. So we're talking about this region here, like this, right? Okay. So as you can see, that's only in that first quadrant. It's only going to be in this first octant, which is why between z and y, I'm only going to be using this side of the hyperbola and only the top half, right? Okay, so let's draw that region here. Got my line, y equals 2x, right? It's this region here, from 2x to 4 on the y. And then the relationship between z and y, right, had no x's in it. So it's a cylinder again, a hyperbolic cylinder this time. So I've got this hyperbola top half thing going on, and it's going to be the same hyperbola sheet over several, stretches there. So what we're looking at is just a piece of this sheet, like this, which is basically overshadowing this region here, right? Just overshadowing this region right here. Okay? And since there's no function in here, it's technically finding the volume, right? It's just a volume integral in this case. Okay? So, real quick, take a look at what it really looks like.
Here's that line, y equals 2x, and we want to go all the way up to the region where y equals 4 here, so that we get that triangular region there. So let's see which one. There we go. Okay. So we're talking about integrating just over this region here of the XY plane. And then the thing that we're integrating underneath is this hyperbolic cylinder here. Notice in the ZY plane here, it's exactly what we have is this hyperbola. Whoops. Right? You can see where the hyperbola shape is here, right? And we're only going to be using this side and the top half. So it's just like what we were looking at before. So we're going to be integrating this section underneath the hyperbolic cylinder there. Okay, so let's take a look at what this would look like. Right, I'm going to have the different wall pieces up here, and that's the top surface piece. And so we've got this chunk underneath the hyperbolic cylinder there. Let's turn off the hyperbola. And then see, this is the thing we're actually integrating over. There's the triangle. And then you can see the way it's curved around the top there, right here, right? You can see the way it curves there. So you can get an idea now of how we're going to be integrating underneath this surface and changing our direction of our variables, right? So instead of integrating the y direction across this piece here, what's actually going to happen is that I'm going to be integrating along the back wall for y right here, right? So even though this is the connection between y and x, since I'm switching variables, you'll find that what's going to happen is I'm going to be integrating the relationship between y and z first. Right, well, not first, I'll be writing it first and then actually integrating it afterwards, technically. So we'll be using this green section underneath the hyperbola there to connect y and z. Okay.
What we want to do is reverse the integral, right? That's our end goal. I've got my three integrals here that I need to do, and it asks for dx, dy, dz. Okay? So let's start with the easiest one, right? Let's do the z. Well, z is just going to go from 0, right, the plane, up to the graph. And at this point, when we're in the outside integral, all of the other dependencies, x and y, have been taken care of. So we just go from the very minimum 0 to the very maximum value there, right? So we're going to start at 0. And then remember, y capped out at 4, right? Y is 4. So if y is 4, what's the height of this piece right here? Well, if I plug in 4, right, that's 16 squared plus 6, 4 squared is 16, plus 4 times 4 is 16. It's just the square root of 32. Which you can simplify if you want to. That's fine, whatever makes you happy. I'm just going to write it for now. So z just goes from 0 to square root of 32. Okay? So then let's keep going inward, right? Y does have that connection with z, okay? But now what we need to have is how is y also connected with x, because I'm going to have to build that too, right? The y connection with x is going to help me do the very final one then, okay? Now, the y and z pieces right here. If I want to flip-flop that connection, right, I'm integrating y in this direction here, basically. Right? I'm going to be integrating the y's sort of like this. Right? From this way to that way. Okay? So that means I have to go from the curve, the z-dependent curve here up to y equals 4. So I know my top limit on y, 4, right? And then I'm integrating this way. So I have to have this curve, but written in the opposite dependence, right? So here, right here, I can easily solve for y in this piece right here. In fact, let's go even one step further up. Remember, all we did was complete the square on this and then square to get the z squared. After completing the square, then what I would do is just add the 4. Square root. And remember, I'm going to keep the positive because we're on that side. Right? And then I have my minus 2. Okay? So I'm going from that curve outward there. So then that's my piece that I need to put here. Negative 2 plus square root z squared plus 4. Up to 4. And then x, right? So x, his dependence basis on y. And before, we were doing it from a y-dependent standpoint, right? That's why the directions are all pointing in the y direction. But now we need to do it the other way, right? If I'm going to integrate this dx, then I need to integrate it in the x direction, this way. Like this, right? So that's going to go from x equals 0, right, over to the curve. Okay? It's going to go this way. So x is going to go from 0. And then that curve represents this same equation here, right? But I just need to solve for x. So it would be to 1/2 y, like that. Okay?